Right. So my name is Philip Chang, and I'm at the University of Wisconsin-Milwaukee. And I'm going to talk about moving mesh hydrodynamics in ChaNGa. And this has been work I've been doing for the last 4 years in collaboration with Tom Quinn at U Washington, James Wadleys at McMaster. And I've also accreted a few other people along the way. The people highlighted in red, Logan Proust and Alexander Spaulding, are my students at UWM. But I'm also doing work currently with Zachary Etienne at West Virginia University, Shane Davis at the University of Virginia, and Yanfei Zhang at the Flatiron Institute. Okay, so I'm going to give a brief outline of my talk. I normally give this talk to astronomy audiences, so I apologize. There's going to be a lack of deep numerical discussion here, but I'll begin with a discussion of basically how numerical simulations are done for astrophysical phenomenon. All right, and basically there are essentially three schemes, right? And for a large part, for most of the time, there's only been two schemes. So there's Eulerian grid codes, smooth particle hydrodynamics, and now this new arbitrary Lagrangian-Eulerian code, right? And I'll talk about pros and cons of these things, right? And I'll talk basically the code that I've been working on called MANGA, which is just a module built upon the SPH code ChaNGa, right? And I'm going to discuss basically three problems that we've been looking at this, actually two problems, okay? So the first is common envelope evolution. The second problem I'm going to talk about is tidal disruption events. And then basically, I'm going to talk about basically work that's ongoing on basically adapting the moving mesh hydrodynamics to general relativistic hydrodynamics, in the hope of basically eventually studying neutron star mergers and stuff, right? And the results of this work, I actually put my original paper, Chang, Quinn, and Wesley, 2017. But basically, here's a list of some of the papers that we've written over the last few years on this. Okay, so to begin, let's talk about basically the basic equations that we're after, which is the Euler equations, right? And so I wrote down two of them. It's actually one more, which is conservation energy. But the first is continuity, which is the mass conservation equation. The momentum equation, which is the conservation momentum, right? And when you write this out, all right, there are two ways of viewing these equations, right? Okay. And in particular, if you look at the continuity and the momentum equation, right, you can break it down into basically a partial respect to t plus a velocity dotted with a gradient, right? And that can be thought of basically as either Eulerian view, right, or Lagrangian view, okay, where basically Eulerian view you take the partial time derivative, and the Lagrangian view you take the total time derivative, right? And the idea is pretty simple, right? So in the Eulerian view, what you're doing is if you're thinking about flow, all right, you're laying it down as some fixed grid. And on that fixed grid, basically stuff goes into the cells and comes out of cells, all right? This is thinking in terms of the fine volume methods and whatnot, right? You're essentially tracking how the fluid flows, right? But there's another method, which is Lagrangian method, which is popular for smooth particle hydrodynamics, where basically rather than thinking about how the fluid flows, you imagine yourself embedded in the fluid, or you are a fluid particle, and you basically are just basically flowing along, subject to basically F equals ma forces. All right, so let's talk about a little about smooth particle hydrodynamics. I got this little picture from Wikipedia because it's nice. All right, so you model the fluids as a number of discrete particles. You can, in principle, you will get the accurate approximation of hydrodynamics when you go to infinite number of particles, but that's not possible using present-day computers, right? And so you have a bunch of these particles which are subject to F equals ma, just basically Newton's second law. All right. Now the issue is that the F part, right, some of the F part comes from pressure forces, and pressure is something that depends on continuum values, right? So like density, for instance. And so you need some estimate of these continuum values, right? Okay. Now we have a bunch of discrete points. It's not in order to generate an estimate, what you do is basically you do a weighted count over some volume. Okay, so you include a weighted count over the nth nearest neighbors over some volume, and you get some idea what the density would look like. Okay, and so the mathematical challenge, meaning computational challenge, actually is doing a rapid search over the nth nearest neighbors. But it turns out that we know how to do this already, right? With n by tree codes, right? So this smooth particle hydrodynamics maps extremely well with n by tree codes, and so for that reason, a lot of the main large-scale cosmological codes, like Gadget or like Gadget, for instance, or Gasoline, or even ChaNGa, right, basically started out as SPH codes because it's actually very easy to put in smooth hydrodynamics once you have an n-body tree code. Okay, now the other way of thinking about this, right, which is the stuff which I think most of us are working on, is the Eulerian scheme, right? And so what you do is you basically break up space into a number of discrete points, right? And again, in the approximation of infinite number of grid cells, you get accuracy. You basically recover continuum dynamics, right? But again, that's not possible, right? And so what you can write is that when you write the equations for hydrodynamics, right, you can write them as a flux conserved equation. What that means is that basically, if you think about these cells, right, there's some stuff in these cells, right, and if you integrate all that stuff, there's some total charge in that cell. Like it could be the total, like if you integrate over the density over the cell volume, it's like the total mass. Integrate basically over the momentum density in that cell, integrate over the volume, that's the total momentum, right? And that charge basically has stuff coming in, which is the flux, and stuff leaving it, which is also the flux, right? And so basically, all you're looking at is essentially the flux conservative equation, which is basically the change in time of some quantity is equal to the divergence of flux, which is basically the flux coming in versus flux going out, plus basically an extra source term, right? And that's basically it, okay? And so basically a lot of this stuff is basically solved, the fluxes is solved using some sort of usually approximate Riemann solver. Okay. Now there's one third last scheme which was not really done in astrophysics for a long time, but is used a lot in basically solid mechanics and whatnot, right? And this is the so-called arbitrary Lagrangian-Eulerian scheme, right? And it turns out that basically what you can do is that like you can actually move the grid along, right? And usually this grid is vector as something like a local quote unquote flow velocity, all right? So this is used in continuum mechanics a lot, all right? I'm going to go back in, so I'm going to start the movie again. So the top picture is basically a piece of steel cutting into another piece of steel, right? And you can see the action only occurs at basically essentially one point, right? Everything else basically the steel is quote unquote just a vecting along for going along for the ride, right? In the bottom picture is basically a bullet that's hitting some liquid stuff, right? Just basically just spewing stuff around, right? So a lot of times these arbitrary Lagrangian-Eulerian schemes, the meshes are unstructured, they have strange arbitrary boundaries, right? Because it's basically mainly for fluid-solid interactions, right? And if you do it right, okay, sometimes there's big speed improvements, especially if the flow velocity is much, much higher than the local sound velocity, right? So I didn't realize this until I started working actually on this topic, right? But arbitrary Lagrangian-Eulerian scheme is used heavily in the defense industry, like tremendously slow, right? So I'll show you a few pictures again. So in the top picture is basically a 3-point shock, okay? You have a shock wave moving in from the left, and it's hitting basically a lighter fluid on top and a denser fluid on the bottom. And because of that, it induces vorticity as it goes around, right? Okay, and basically you're trying to follow this, you're trying to cause the mesh to basically follow the fluid flow, right? As go, and you see what happens basically. The mesh starts to get really, really distorted, right? And so basically to correct this, right, you need to usually remesh this stuff. And there are lots of literature basically associated with, especially in defense and the national labs, discussing how you do this remesh, right? Okay, but the basically idea is you let things flow, the mesh starts to get tangled, all right, and once the mesh starts tangled, you basically want to remap it, and you remap in one way, two ways. One is that you could just lay down a new mesh and remap all the points. The other way you could do is basically you could have the mesh relax basically back to its original phase, right? And so this remeshing typically is a numerically pretty diffusive action, all right? And so that sort of defeats some of the purpose of basically these arbitrary Lagrangian-Eulerian schemes, right? And for in large part, basically, this was not widely used in astronomy until about 2010, all right? And the key development was basically a development of numerical hydrogen on Voronoi meshes, which basically not solves the problem, but basically um, um, allows the problem of remeshing to basically happen in a continuous fashion. right? So let me talk about that briefly. Okay, so let me talk about Voronoi tessellation, right? So suppose you have an arbitrary distribution of points, right, in space, and you want to basically divide up space in via using these arbitrary distribution points. So how will you do that? Okay, so it turns out there's a tessellation known as the Voronoi tessellation, where in order to do this, what you would do is you basically pick 2 points, right, any two neighboring points, and then between these two neighboring points, you would draw a perpendicular bisector between them, right? In the case of 3D, it'll be a plane then. Whoops, where's my mouse? Sorry, it'll be a plane. Okay, if you draw a perpendicular bisector, and then you basically continue this operation. So you basically pick the next 2 points, draw a perpendicular bisector between them, draw the next two, pick perpendicular bisector between them, and so on. And when you do so, right, you will get a tessellation of space, right, where every point in that cell is closest to the point that is defining the cell. And the tessellation has three unique properties, which is important, right? The first one is that the tessellation is unique, right? There's only one way of drawing this tessellation when you do this. The second important thing is the cells are convex, right? Which essentially means that basically everything in the cell is closest to the point that's defining the cell. And thirdly, the most important thing actually is that as the cell deforms, as the points move, the cell will deform continuously under small perturbations, right? And you can see this basically in this picture I have on this on the left. We have a small blue dot moving across this Voronoi tessellation, and the tessellation doesn't change every time the dot moves. It basically slowly evolves as it goes across, right? And so these well-defined faces, well-defined volumes, and basically slow evolution of these faces and volumes allow finite volume methods to apply this. And this is what Volcker-Springel basically discovered or rediscovered in 2010, right? And so what's also interesting is that basically any flux conservative equation can be solved using in these moving unstructured meshes, right? And so there's been a huge explosion of basically moving mesh codes based on this methodology in astrophysics at least. REPO is basically Volker Springer's code. There's also RICH, all right, Rockout Institute Computational Hydrodynamics by Sternberg. There's TESS by Duffel and Mafagian, and then there's MANGA by myself, Tom Quinn, and James Wasley. Okay. Let me talk a little bit about pros and cons of Voronoi hydrodynamics, right? So there are a few great things, right? So because the mesh can move with the flow, you don't have to have so much advection, right? And so basically you get better advection than Eulerian, right? Just because you don't have to do so much, okay? In principle, you can have better conservation of angular momentum compared to Eulerian schemes because you just don't have three special directions. The directions are arbitrary, right? You definitely have superior shock capturing compared to SPH. SPH tends to basically smooth out shocks over several smoothing lengths, right? In this case, basically, if you use a Riemann solve, you can just capture it basically in one cell, right? You potentially have better capture of interface instabilities. This is in principle. This is a debatable point because it's not entirely clear that like moving meshes are actually better, but they certainly look better in a lot of basically comparisons, right? You can do MHD, right, in the moving Voronoi mesh, unlike SPH, though that point would be debated depending on who you talk to. Those people, unfortunately, I believe are wrong. Okay. You have continuously varying resolution. So rather than basically having jumps of basically factors of 2 and 4 between cell boundaries, the resolution can vary continuously. Okay. And almost anything that's solvable on Eulerian grids maps to Voronoi methods, right? That's one. That's the pros. The cons is that basically they're far more complex, all right? A combination of Lagrangian schemes and Eulerian schemes, plus computational geometry make the codes a little more hard. You start to force yourself to think about the grid now. Unfortunately, you got to think about basically how you want to map things onto a grid, which has pluses and minuses. This forces you to think a little harder. On the other hand, basically, it also basically opens up a whole other can of worms. It's quote unquote slower. I put that in quotes because basically in my testing, comparing to SPH, it's not necessarily slower, right? The heavier computational side is offset in large part by basically higher resolution per point and also a larger cron time stepping typically. Um, The other thing is that like MHD is usually divergence cleaning space schemes or vector potential based schemes, right? So no staggered CT scheme, which is like the gold standard for MHD, exists in these methods, right? And finally, there might be overkill for some of these problems, right? However, I would say that like the advantages in vection, shock capturing, and basically conservation law make it great for dynamical stellar problems. Basically, stars hitting each other, stars basically getting ripped apart, that kind of stuff, right? It's also used for galaxies, but that's not my forte, so I'm not really discussing that. I'm going to talk a little. MANGA is based on a Voronoi hydrosolver for charm plus n-body gravity, or the ChaNGa code, which is n-body SPH code. It basically uses the charm plus programming model. Everyone knows what charm plus is. This is there because usually it gives this talk to astronomy people. Like, what's charm plus? I have no idea. Like basically makes it easier to write hybrid codes essentially. All right, and ChaNGa. All right, this is a very old plot now, like 2014. All right, but it's still true. ChaNGa still is pretty well in pure gravity up to about 500,000 cores, 93% efficiency. Right. Okay. Here's a little bit of basically some of the physics that we have in MANGA now. So we have, oh, this is all messed up. All right, so I got to talk about. So in the left top thing is actually should say hydrodynamics at the end, but this is what happens when you use Linux presentation software. So this is a state of explosion. Okay. On the top right is self-gravity. Okay. On the bottom one is a stellar equation state. So we have different equation states for this one. This one's an interesting equation state. If you are eagle eye and you look in the bottom, you will notice this star is only about 10, 15 kilometers in size. This is actually a neutron star. And the equation state here is a nuclear equation state we adapted from basically from literature and we put it in MANGA. So there we have a bunch of different stellar equation states in MANGA, including basically, well, like stellar equation states for white dwarfs and for regular stars and for planets, etc. Okay. There's some other physics that we have involved as well. One is radiation. MANGA is in fact a full radiation hydrodynamics code, right? And for those of you who can see this, right? You will notice that basically what I have is I have two light beams basically crossing each other, right? And this turns out to be a really hard problem. And it's actually most radiation hydrodynamics codes will fail at this task. Okay, mainly because a lot of times they either use methods called flux limit diffusion or moment one methods, right? Which basically do not either in the flux limit diffusion do not allow basically beams to exist, or in the moment one method only allows basically one beam in one direction to exist, right? And so basically you have crossing beams, that's kind of nice, all right? So what we have is we actually solve the full time-dependent radiation equations, but using in the reduced speed of light approximation in order to keep the time step from going crazy. And the other one that we are able to do is basically we can do some GR hydrodynamics in static spacetimes at this point, right? So this is basically work that I recently did with Zach Etienne. Okay, all right. So let me talk a little about some of the current features. This is basically was highlighted in the previous slide, but then a little more detail here. We have hydrodynamics on the Voronoi mesh, self-gravity. So with self-gravity, we have either entropy or energy solving, depending on your choice, right? We have a multi-stepping scheme, so every single cell has its own time step, all within a factor of 2 of the global time step. We have a all within steps of factor of 2 with the global time step. We have different equation states, including Mesa equation state. We have basically what's called moving and reactive boundaries. I'll talk about that later. We have radiation hydro. We have GR hydro on the moving mesh as well, okay, in static spacetimes, right? In terms of near-term goals, we're basically hoping to get open source version out by early or mid 2021. There's no showstoppers here. It's just that like I'm just lazy. The other thing is that we're also working on constrained transport, all right, for MHD. And we also are working on basically moving mesh GR hydro, hopefully for binary neutron merge. This basically involves adapting a dynamical spacetime solver and putting it into MANGA. For longer term goals, we're hoping to basically do higher order spatial reconstruction methods, right, in the not too distant future, perhaps core collapse supernova or moving meshes with neutrino radiation, and for point source radiation as well. That one's like, it's not, that one's actually more straightforward. It's just that it's not on my immediate to-do list. Okay, let's talk about common envelope evolution, some of the applications of this. All right. So what's common envelope evolution? Since most of you are computational people, I'll just talk a little about it in terms of astronomy. So you look up at some of the most interesting systems in the universe. These are basically stars that are really close to each other, and they're usually like compact stars, like either white dwarfs, white dwarf, neutron star, neutron star, neutron star, white dwarf, or black hole, black hole. Like, these are stars are really close to each other, and they're, when they basically are close to each other, they can do interesting things, right? Now, the problem is that how do you get them close to each other, right? Because stars, when they start out, they're actually relatively big compared to white dwarfs or neutron stars or black holes, right? And one of the leading ways of thinking about this is that basically what happens is that they undergo something called common envelope evolution, where basically a star, hold on a second, I need to tell someone not to call me. I don't know why. I'll kill it. Okay. Um, sorry, I apologize for that. And okay. And so what happens is that as a star evolves, basically it goes to the red giant branch, and if this neighboring star is close enough, it can actually basically fall into this envelope. And when it does so, basically the star basically interacts with the envelope and basically expels that envelope. And in doing so, it basically converts its gravitational potential energy of the orbit to basically expelling the envelope. And in doing so, it basically reduces the orbit of the two stars, right? Such that they can get close to each other. And these pairs of binaries are perhaps very important. They can basically produce supernova, they produce millisecond pulsar, they produce basically binary neutron stars and binary black holes, which is very interesting for people who are gravitational waves right now. Okay, so here's basically an example of that what we've been doing with MANGA. So you have two cores which are denoted by the X and the cross, and then the big star is the center mass of the system. And what happens is that basically we start out basically a red giant star with a 52 solar 52 solar radii and a 1 solar mass secondary, right? So we treat as basically a dark matter particle. And we basically let these things orbit each other, and we run this for basically 240 days, not in computer time, but in basically system time, right? And basically 110 of these days is shown here, right? And the question is basically, does the envelope get ejected, and how close does it get at the end? And the answer is that basically what we find is that in large part, we can jet most of the envelope, assuming that we can basically take account of the internal thermal energy. So basically, if we take account of the internal thermal energy, we get something like 66% of the envelope is ejected, which is great, okay? And the envelope and the orbit shrinks substantially. It goes from basically 52 solar radii all the way down to about 3. Okay, so that's pretty good as well, all right? Now, there is a question here, which is basically, can you actually include the thermal energy? All right, and the argument against it is that basically, well, if you try to include thermal energy, what happens is the envelope expands and then it can cool, and then basically it cools, all that thermal energy goes away as radiation and actually act as a way of expanding out that envelope, right? So we're basically working on that problem as well, thinking about basically ways of including cooling effects in the envelope to see basically how much of this envelope ultimately actually ends up getting ejected, right? The other thing I want to talk about, this is work mainly done entirely by my student, right? Is that if you think about it, all right, you have a red giant. The red giant is kind of big and poofy, right? And then you have a solar mass star like sun. And relative to the red giant, the sun is like a big dense object, right? And so if you think about it, you can think about basically what if you place the big dense a marble and have a circulating rising around this star, okay? What happens? Well, right now we've been treating things as a dark matter particle, which basically it doesn't interact with matter at all. But if you think about it, what happens is that the gas can basically hit the secondary star and bounce off, right? Okay, so and that hydrodynamic flow is not really accounted for in current models of common envelope evolution. And so that's basically one thing that we want to think about, was that basically, can you basically put arbitrarily shaped boundaries, right, with arbitrary boundary conditions inside the simulation, right? And so this is one thing that we've been doing, which is called moving reactive boundary condition. The secondary star itself is a boundary condition, a reflecting boundary condition, and that reflecting boundary condition basically realizes the forces are acting upon it and basically moves the second star with it, right? And so basically, this is an example of this problem right here. What I have is basically a wall hidden basically between position x equals 3 and x equals 5. And then I just set off a quote unquote a Sadov 1D Sadov explosion on it, okay? And then as you can see, what happens once it hits the wall, right? It's going to bounce off the wall, send back a reflecting shock, right? But the wall will basically move and basically send a forward shock basically through that material as well, okay? Right. And so we've been doing this basically common envelope with a hard secondary. So basically moving boundary condition run with the same initial conditions that we did earlier. And we get basically a somewhat different in spiral, though right now, given the stuff that we've done much more work since this time, we don't really think it makes a huge difference for the common envelope evolution. All right. But more analysis remains to be done. Okay. All right, so I'm going to talk about my next problem. Let me see how much time I have. Am I out of time? I might be. So I'll skip.
A couple more minutes. Yeah.
All right, so I'll skip this thing. All right, so tidal disruption is like stars get ripped up by black holes, right? And then let's show a movie. Here's a star. It gets ripped up by a pole. It gets basically spewed out, right? This is interesting. And then you have accretion onto the black hole as well. And so what we've been finding is that basically what we're interested in is basically how is this material distributed in energy space afterwards as a function of how deeply penetrating it gets in. And basically what we find is that basically it rises for some period of time and then basically gets cut off, right? And that cutoff is known as frozen in approximation. And so we have a pretty good understanding of how this thing works. Now, this is important based understanding what the accretion rate onto the black hole is going to look like. All right. Last thing we'll talk about is general realistic hydrodynamics on the moving mesh. All right. So as I talked about before, any equation can be solved on the moving mesh that we've written as a flux conservative equation. And so basically on the top, I have what it will look like for hydro, and the bottom I wrote what it looks like for general realistic hydro, right? So it looks almost the same, all right? Same in quotes, right? And so you could basically solve it using the same methodology as before, right? And so this is basically what we have done. So this is a Tolman-Oppenheim-Volkoff star, which is essentially a neutron star on the moving mesh, right? So we model this thing with about 1 million mesh generating points with basically 1 million more filling the atmosphere, right? And we have a fixed basically metric, and we just run this for basically 24 dynamic times. You can run it for longer if you'd like, right? And what happens as a function of resolution, this is shown on the right plot. As a function of resolution, basically, there is a difference in terms of basically how much the central density drifts as a function of time, right? And as a function of resolution. Namely, at higher resolution, basically it drifts less. Now, this is understood, right? And so we get a 2% drift with 1 million particles or so, all right, over 24 diameter. This is terrible compared to basically what grid codes are able to achieve, right? But we know what the problem is. Actually, is basically these single star evolutions are extremely sensitive to spatial reconstruction. And for these moving mesh methods, thus far, the only reconstruction method that's been really developed is second order. And so you probably need to go higher order basically too, right? So this may be fixed in the near term with developments in unstructured higher order methods, which I don't know much about, but I'm hoping to learn more about it. Okay, and basically this is another thing that you can do, but just to test it out. You can reduce the pressure of the entire star by 10%, and the star will just begin to oscillate radially at the fundamental mode. And we can compare that to basically a known solution from a known code, Illinois GRMHD, shown in a dotted line in the right column. And you can see basically the fundamental mode is more or less recovered for all different things, either in multi-stepping or in single time stepping, right? So the future, we're going to basically try to include a dynamic space-time solver and a MANGA for full moving mesh binary neutral star simulations. All right, these are my conclusion slide, and I'll just stop here.
Thanks, Philip. We do have one question in the chat from Mike Norman.
Okay.
Yes. Do you use a fixed or variable number of generating particles for your Voronoi mesh? If fixed, how do you deal with the very low density regions, which would be undersampled?
Uh, I'm not sure what he means by fixed or variant. I think we can use an arbitrary number of particles, and what we do is basically we don't fix them anywhere in space. We change the resolution as we go outward. So the key with these moving mesh methods is that not to have sudden changes in resolution. And so as we move away from the point of interest, we basically increase the spacing between these particles so that basically so that you don't spend too much time like computing stuff you don't care about. All right, with too many particles, but you also want to avoid basically sudden changes in resolution as well. And I saw someone raise their hand, but I
Yeah,
have no control over anything. So
Tom Quinn, you can go ahead and ask if you can unmute.
Hey, Phil.
hey,
Great stuff you're doing. So, do you have any scaling plots? I mean, how?
I don't. Scaling is a slight issue right now. So why is that? So the thing is that like for every computational step, all right, I have to do, I think right now it's 3 nearest neighbor searches, all right? Whereas basically in SPH, you got to do just one, right?
Right, we actually
Uh,
two actually, but
you're
yeah.
actually doing 2? All right. Okay, so I got to do 3, okay? So that I think is the limit of the scaling. Haven't done a huge amount, and part of the reason why I've been focused much more on implementing different physics into the code right now. All right.
Mm-hmm. No, that's it's great. You're doing that. This is wonderful. Yeah.
One last question from Neil Stepp. He said current codes use an atmosphere treatment. Is that still necessary? And if so, how low of an atmosphere can you use?
So the answer is that any Eulerian code will need an atmosphere treatment. So yes, we still need atmosphere treatment. No, any grid-ish code will need atmosphere treatment. You can't have vacuum basically. So yes, we do need that still. So I believe so for the so there's 2 answers to this. So for the star, when like tidal disruption or common envelope, we can go about 15 orders of magnitude difference. Okay. I for the GR hydro right now, I think I'm down to about 7 orders of magnitude difference. All right. Between the central density of the star and the atmosphere. All right. Maybe it'll go lower than that, but starts becoming unstable actually after if I go much lower.
Okay. Yeah, I think you need about 16 orders of magnitude
For
for the relativistic case. Current
well,
state-of-the-art codes use
yeah.
about 10, and that's still not quite enough.
Right. Okay. Well, okay. So I mean, like, I thought you were about to say there's a code out there that can do 16 orders of magnitude difference in the relativistic. I was like shocked. But yes, you're right. Yeah. So yeah, you do need that.
There is a code that can do 16 orders of magnitude.
Oh, really? Which one is that?
It's by David Radici.
Okay.
So they basically use a flux limiter, a positivity preserving flux limiter.
I
And so
see.
they don't, so I'm trying to
Interesting.
remember if they were able to do magnetic fields with that or not, but without magnetic fields, at least they can do 16 orders of magnitude.
I see. Okay. All right. That's interesting. All right. So I know you're part of the Spectre group. Is that right?
Yeah.
And how many orders of magnitude can you do right now from Computer Center?
We're trying. So we're trying to do DG, and that's even harder. For DG, we've basically given up on using DG for high order hydro because you basically can't go beyond second and third order, right? So it seems to be good for sort of where the solution is smooth, but basically all the limiters in the literature to handle discontinuities are basically worked out for Newtonian hydrodynamics on Cartesian grids, and we want to do curved meshes with relativistic hydrodynamics, and it turns out they just don't translate. So we've basically switched to a finite difference DG hybrid method. We have not tested the relativistic case. In the non-relativistic case, so the Lane-Emden stars were able to do 24 orders of magnitude.
Right. Yeah.
But
Okay.
how that translates to the relativistic case is to be determined, hopefully soon.
Yeah. Right. Okay. Well, thank you for that note. That's interesting. Flux.
Yeah, no, I mean, I was
yeah.
just curious because
Yeah.
I have not personally, I personally have no experience with these like truly moving mesh, right, where like you follow the fluid. So we use a moving mesh, but we basically it's basically to capture the rotation and shrinking of the orbits
Yeah.
as the neutron stars orbit each other,
Right.
but it's not to track the fluid motion. So
yeah, it's the same as the old spec code, basically, right?
yeah, exactly. Yeah.
All right.
Yeah. The big difference is we're treating the Einstein equations and the Hydro equations on the same grid,
Right.
as opposed to in spec where they're on two different grids, and that interpolation adds an enormous amount of computational overhead. So that's sort of the big difference. But yeah.
I'll ask that you take more conversation into the chat or offline, and we'll move to our next talk. Thank you, Philip, for the
All right.
presentation.
Thank you.